This is a fluidized gasification system which heats up a fluidized bed at atmospheric pressure to produce syngas. As syngas is produced, some of the fluidized bed particles become entrained within the syngas. These particles need to be separated, therefore a cyclone is positioned downstream of the gasifier. This allows the lost bed particles to be recycled back into the bottom of the gasifier. Meanwhile, the cleaner syngas is released from the top of the cyclone. The fluidized bed which forms at the bottom of the gasifier consists of bed media such as sand and limestone. The sand helps to distribute heat evenly, and the limestone helps with sulfur reduction. The feedstock is the fuel source and is commonly wood chips or pellets. In order to create the fluidization of the bed, a mixture of air and steam is used at high velocity. Air provides the oxygen necessary for the partial or incomplete combustion to produce carbon monoxide. Steam reacts with the char and other components to produce further hydrogen and carbon monoxide. As the fuel moves through the bed, it passes through several stages. The first stage is drying, where any moisture within the feedstock is driven off. The next stage is pyrolysis, which takes place when biomass is broken down into volatile gases, tars and solid char. Then gasification takes place, where char reacts with oxygen, carbon dioxide and steam to form carbon monoxide, hydrogen and some methane. Finally, at the bottom of the gasifier is where combustion occurs, producing carbon dioxide. Together, this mixture forms syngas. As syngas is produced, some particles can become entrained within the gas stream. These particles must be recovered so that the overall efficiency of the process can be improved. This is achieved using a cyclone separator. The gas mixture flows upwards and out of the gasifier. The gas then enters the cyclone tangentially, and as the gas spirals downward, the heavier particles experience centrifugal force and are thrown outward toward the cyclone wall. The solids lose momentum and fall downward into the collection leg. These solids are then fed back into the gasifier via a feed pipe or conveyor, which allows unreacted char to continue gasifying. It can also recover bed media such as sand, which may be entrained within the gas stream. Meanwhile, the cleaner syngas reverses direction and exits at the top of the cyclone, where it can be further treated downstream before it is used for real-life application, such as hydrogen production. The first key reaction in gasification is partial oxidation. Here, solid carbon reacts with a limited amount of oxygen. Because there isn't enough oxygen for full combustion, the carbon doesn't just form carbon dioxide, it also forms carbon monoxide. This reaction is exothermic, meaning it releases heat, and that heat is crucial because it drives all the other gasification reactions inside the reactor. Next is steam gasification. In this reaction, hot steam reacts directly with solid carbon. This produces carbon monoxide and hydrogen, which together make up syngas. Unlike partial oxidation, this reaction is endothermic, so it needs heat, and that heat comes from the partial oxidation reaction we just discussed. The water-gas shift reaction happens in the gas phase. Carbon monoxide reacts with steam to form carbon dioxide and additional hydrogen. This reaction is reversible, meaning it can go in either direction depending on temperature and steam content. It's especially important when we want to increase hydrogen production or adjust the hydrogen to carbon monoxide ratio of the Syngas. Steam reforming targets hydrocarbons like methane that are released during fuel heating. Methane reacts with steam to produce carbon monoxide and a large amount of hydrogen. This reaction is strongly endothermic, so it only occurs at high temperatures. It plays a key role in boosting hydrogen content and preventing valuable fuel from leaving the gasifier unconverted. If you enjoyed this video, please make sure to comment, like and subscribe.